chapter 2. So atoms and elements. So today we're going to be learning, oh, I shouldn't go away from the laptop. So today we're going to be learning more about actual chemistry rather than just units and measurements. So it's going to be more interesting and we're going to learn a lot. So we'll start off with the basics. Now, we can't have a study of matter without having fundamental laws. And there's 3 really fundamental laws that govern the chemistry and the chemical reactions that we use in this class. And the first one is the law of conservation of mass. So when I have notes like this up, you don't have to write down every little thing. It's going to be recorded for you. So just understand what it means. So law of conservation of mass. So matter in a chemical reaction cannot be created or destroyed in a closed, well, really in any system. But so if you have a closed system that you can have no way energy or mass escaping during a chemical reaction, the amount of reactants you have that mix together to make a new substance is going to be exactly the same mass as the product, as the finishing product. So let's say you're adding 5 grams of sodium to 5 grams of chlorine. Let's say they go to a 1-to-1 mass ratio, which they don't. But let's say they just add together. 5 plus 5, 10. So you're going to get 10 for your product, even though that's not what happens. But just to give you an idea of how the law works in terms of the conservation. Now, by that metric, you can say that the entire universe has a fixed amount of matter. And that's true for the most part. And I mean, we're not dealing with quantum things. So technically, the law of conservation of mass is up for debate now. It's a weird fact. But you can actually make new mass and new matter. It's weird, but based on like dark matter and things like that. But we're not going to talk about that in this class. I don't really know that much about it. My knowledge is very limited. But in general, the universe has a fixed amount of mass and a fixed amount of matter and a fixed amount of energy. So these are universal constants that you cannot create or destroy. You cannot create more out of thin air, and you cannot destroy some into oblivion, into non-existence. So it's a definitive trait for any reaction. You can't add or subtract and have it disappear. Okay, so here's an example of that. So you have, NaCl. So here's the correct ratio that sodium and chlorine add together. So you have Na, which is just a metal, right? We're going to learn about the different traits of the periodic table today and the different traits of the elements that are on it, the way it's organized, and things like that. And also you have chlorine, which forms naturally a diatomic gas. So chlorine naturally forms a Cl2, just like oxygen, just like nitrogen, just like fluorine, just like, that's it, bromine, I guess. But yeah, so you're going to add 7, let's say in this hypothetical reaction, you add 7.7 grams of sodium to 11.9 grams of chlorine. You're going to end up with 19.6 grams of NaCl, and you see the mass is conserved. So mass of the reactants equals the mass of the products. Okay, so the second law is the law of definite proportions. So this is one that's kind of like, oh, duh, but I have to explain it anyway. So basically what it says is that all samples of any compound, any one compound, let's use water as a very easy example. So we know water is H2O. Any source of H2O, whether it be from the ocean, from the lake, from your water bottle, has the same proportion of hydrogens to oxygens, either by number of atoms, by mass, very same thing. And that's a definite proportion for that compound. You can't have water, H2O, that acts the same, exactly the same as water. Oh, this one happens to be H3O, or this one happens to be HO. That's not how it works. So if you do have that, there are compounds H3O. H3O is called the hydronium ion. It's H3O+. And then OH, let's say you get rid of a hydrogen, it's hydroxide ion. So once you remove or add an atom from a molecule, it becomes or a compound, or really any molecule, it becomes a different chemical substance. So this law is stating that the chemical substances that are the same, meaning water from here, water from there, is going to have, or are going to have, the same exact chemical formula. So that to most of you is, oh, duh, that makes sense. Yeah, and yeah, it does. But that needs to be established before we learn more about chemistry. So here's an example of the constant mass ratio between oxygen and hydrogen. So for H2O, there happens to be, and we'll learn about molar mass in this class, a very big, important skill, which we need for everything else in this course. So the molar mass of oxygen happens to be 16 grams per mole, about, and for hydrogen, it's about 1. So if you have H2O, you're going to have 2 hydrogens. So 2 plus 1, no, 2 times 1 is 2. And then you're going to have 1 oxygen, which is 16. So for the compound of water, you can say that the ratio of oxygen to hydrogen by mass is 16 to 2, or 8 to 1. And that ratio, that definite proportion, is constant. My mask keeps falling down. Is constant for any source of water you find. So that's important. So there it is in action. All right, cool. You could do the same thing with NaCl. Fantastic. Cool. Whatever. Any questions about those two?
Professor?
Yes.
It's not about the class, but I was trying to join from the week 1 module, and I think you marked me absent. I also emailed you. I should have done it sooner, but it kept saying like waiting for the host to start the meeting.
Oh, that you probably picked the wrong link from the announcements.
Yeah, so that's my mistake.
Yeah, you're fine.
So,
you guys are fine. So
yeah, my name is Yahya. If you need.
Yeah, I got you. You and Justin, same thing. All right.
Yeah,
so
thank you.
For now, yeah, just so everyone's here now. The links are going to be in the module. And it's actually going to be the same link. All I do is drag it from module 1 to module 2. So so now you all have it. So just do the same exact thing. It'll be the same exact link even. So, okay. Thanks for letting me know. Good job. Okay. So the third law is a little bit more complicated actually. And it actually took me some time as an educator to figure out a good way of teaching it. And it's very elusive. So it's the law of multiple proportions. So in 1804, John Dalton, he made the Dalton's chemical or Dalton's atomic theory, which we'll learn in a second, is the law of multiple proportions, where basically we'll read off the slide and I'll explain it. So you have 2 elements, right, A and B, that they form different ratios and different compounds, so different combinations. Let's say it's, well, there's a question. Let's say it's AB1. Could you zoom in on the slide? Oh wait, you guys see the, I'm not sure what you guys see. Screen share. Aha, there we go. Perfect. That should be a lot better. All right, so there could be different ratios of A and B. So it could be AB1, AB2, AB3, meaning there's 1A and 1B, 1A and 2B, 1A and 3B. For example, there could be hundreds of different other combinations. But in these ratios, each one of these compounds has a ratio of the mass of A to the mass of B. Or in the way they word it is the masses of element B that combine with 1 gram of element A, meaning the ratio, basically the mass ratio. Each one has a mass ratio of A to B. Those mass ratios are whole number multiplicities off of each other. So meaning, and they show an example. Well, let's just go by example. That's the best way to do it. So here's an example with just using 2 very simple compounds, carbon monoxide and carbon dioxide. So the mass ratio of oxygen to carbon in carbon dioxide is 2.67 grams of oxygen to 1 gram of carbon. So that ratio is a number, 2.67, not a whole number, just a decimal, fine. Then the ratio of carbon to oxygen, or sorry, oxygen to carbon in carbon dioxide, oxygen to carbon, yeah, okay. So the same thing for carbon monoxide, for oxygen to carbon, is 1.33. So 1.33 grams of oxygen to 1 gram of carbon. Another ratio, 1.33. So the idea of this law of multiple proportions is saying that once you have these multiple proportions of element A to element B in different compounds, they are whole number differences from each other. So if you divide those two proportions, 2.67 divided by 1.33, you get 2. So this works for really any combination of element A and element B. It even works with more than 2 elements. It works with 3 elements too. So, but that's more complicated. There's a lot more combinations. But that's what it means. So a good question that a lot of students ask is, why is that important? So it's important to establish this. And a lot of you, maybe you're thinking, because you're more engineering math minded, it's like, all right, I get it, but why, like, what's the significance of it? Not really why it's important, what's the significance? So the significance is that these compounds can't obtain ratios of A to B that have like 1.5 atoms. There isn't CO 1.5. There isn't CO 3.5. They have to be whole number ratios of element A to element B. And those whole number ratios of masses then can divide into let's say the second compound with the same elements to get whole numbers. So that's proof that you can't have a weird fraction of atoms in a compound. So that's what this law is mainly for. So is there any questions on that? I know it's a little complicated. I'll show another example. So here's another example with 3 compounds with nitrogen and oxygen. So nitrogen and oxygen form 3 major compounds: nitrous oxide, which is N2O, nitric oxide, which is NO, and then nitrogen dioxide, which is NO2. And you can take the ratios. It doesn't have to be of nitrogen to oxygen. It could be to oxygen to nitrogen, and you'll still get the same answer.
Is all wrinkled.
Can whoever is talking
Sorry, I'll take care
mute,
of it right
please?
now.
Okay, I did it. All right. So you can do the ratios of atom A to atom B. Let's say in this case they do the mass of nitrogen to 1 gram of oxygen, and then you divide these ratios by each other, and every single time you'll get whole number differences. So that's that. Yeah. Any questions on that? No? Okay. All right, moving on to Dalton's atomic theory. So Dalton had these, there's actually 5. Some textbooks say there's 5, some textbooks say there's 4. I learned there's 5, but sometimes they condense the 4th one, they condense the 5th one to the other ones. I don't know, but anyway, in this textbook it teaches 4. There's 4 postulates of Dalton's atomic theory. And no, you don't have to memorize each one. You just have to understand what they thought at the time. So he proposed this theory saying that each element is composed of tiny indestructible particles called atoms. That's true. Second one, the atoms of a given element have the same mass and other properties that distinguish them from atoms of another element. That is also true, because we know based on the periodic table, there are different types of elements, and they all have different properties than another element. 3, atoms combine into simple whole number ratios to form molecules of compounds. True. It should be molecules or compounds. Who wrote this? Did I write this? Maybe. So that's based on all the different laws we saw, that you can't have 0.5 of an atom. So that makes sense. 4th one, which is the one that's a little bit, we don't know, is in a chemical reaction, atoms of one element cannot change into atoms of another element. Now this one was true for a while because we didn't know anything about nuclear reactions. But now we have a plethora of information on nuclear reactions, radioactivity, which elements can react with other elements under high energy and high instability to actually break their nucleus and form different elements. So we see that all the time with like nuclear power plants, for example, nuclear fission. So yeah, so that was true, but that's a really good start. This was early 1800s. He figured this out. So that's a really good start. Okay, so let's get into the nitty gritty. Now, the periodic table symbols, it's very important to understand the different numbers on the symbols. Now, the first one is the top number, which is the atomic number, and it is in bold for a reason. It's very important to understand the top number is a whole number all the time, and it represents the number of protons. This is the main way that the periodic table is arranged. So if you look at hydrogen, helium, lithium, beryllium, it goes 1, 2, 3, 4. And you kind of read it like a book. It goes from the top left all the way down, and you read it from left to right, up to down. And that's the number of protons. So we'll be learning about, today we'll be learning about actually both ions and isotopes. Now, isotopes, maybe if you heard from freshman, or not freshman chem, this is freshman chem, you heard from high school chem, that they have different number of neutrons. And then when you deal with ions or things with charges, atoms with charges, you have a different number of electrons. You notice that the protons don't change in any of these two phenomena. And that's true. The number of protons of an element cannot change. If it does, let's say by nuclear reaction, it becomes a different element. So the protons, or the atomic number, is the strongest characteristic of an element. You can't have a chlorine with 18 protons, then it's not chlorine anymore, then it's neon. No, then it's whatever, xenon. Yeah, neon's 10, so that's xenon. So the protons are characteristic of the element. So then the bottom number, which is usually a decimal, when you get to the weird elements like unununununquium, all those ones that are like 116, 117, all those weird ones, they are whole numbers. And the reason why they're whole numbers is because only one isotope has been discovered, and we don't really know the exact mass of it because it was created in a laboratory, synthesized for like a nanosecond. We detected it and then it disappeared, or because it was so unstable, then it became radioactive and the nucleus exploded. So we don't really have sufficient data for those high proton elements, the ones that are towards the bottom right of the periodic table, to tell the average atomic mass. So we'll talk about this average atomic mass right now. What it means is, it is a weighted average of all the different isotopes that are naturally abundant of that element. So what isotopes are, which we'll cover in the next slide, isotopes are versions, let's say, versions of the same element that have a different number of neutrons and therefore have a different mass. So these different masses, these different types, isotopes, isotypes, these different types or versions of the same element occur at different ratios in nature. And really it varies based on the stability, based on what is more naturally selected, I guess, in chemistry. So for chlorine, for example, there's two main isotopes. There's chlorine 35, which has a mass of 35, and chlorine 37, which has a mass of 37. One of you is, I could read minds. One of you is probably thinking, what happened to chlorine 36? Well, that's a good question, actually, but it just so happens, energetically, chlorine likes to have, how many protons? What's 37 minus 17? 20, yes. Yeah, okay, I could do math. So 20. So chlorine either likes to have 20 neutrons or it likes to have 18 neutrons. Why doesn't it like to have 19? I don't know. Just energetically, it works out better when it has 35 mass or 39. So these natural abundances, chlorine 35 is more abundant, 75.78, and chlorine 37 is less abundant at 24.22%. Now, these percents can be taken as a weighted average, and that weighted average is the average atomic mass. So by weighted average, I mean what you do is you multiply the mass by the percentage that it occurs, and then you add it to the next one. So kind of like how you would calculate your grades. So I'm sure a lot of you were stressed out about grades in high school, and it all paid off because you're all in a very good school. But when you calculate your grade, you're like, oh, homework counts for 20%. So my homework grade times 0.2 plus, oh, the tests were 80%, 0.8 plus times my test grade, all that stuff. That's how you find the weighted average. So maybe I was a little bit more manic about my grades than you were, because I did that for like all my classes. But that is how you calculate the weighted average when it comes to isotopic abundances. So is there any questions on that math or or really anything I said so far? What? Oh, AMU, good question. So AMU is the atomic mass unit. So it's really the unit so it's a very, very small unit, and it's what we use to represent the weight or the mass of a of an atom or atoms. So the conversion is actually, I don't even know the conversion off the top of my head, but it's like 1 AMU is 10 to the negative 34 kilograms or something like that. So it is a very small unit, but we are going to scale this unit up into our grams per mole, which is what we're going to talk about for a lot of the class today. So the reason why we do this is so we have tangible samples of matter, so that we can do reactions with, we can see the reaction outcome and explosions and stuff like that. Okay, so so isotopes, they are the same type of element with different masses, and what the different masses mean is they have a different number of neutrons. So that's important. Now, I know we didn't, I don't like the way this lecture is outlined, but it's the way the book does it, that we didn't really cover exactly protons, neutrons, and electrons, but basically you have the protons and the neutrons, which are in the nucleus, and the electrons are floating around outside of it, going really, really fast, but their mass is considered negligible in this class. It's very, very small. So with, let's say, chlorine has a light isotope and a heavy isotope. Every single isotope of chlorine, as you see, will have 17 protons, because that is the atomic number for chlorine, it's 17. And then the neutrons will change based on the type of isotope, whether it's chlorine 35, it will have 18 neutrons, chlorine 37 will have 20 neutrons. So it varies. And then the mass number of each isotope is calculated by, you can see, the protons plus the neutrons. So 17 plus 18 for the light isotope is 35, and 17 plus 20 for the heavy isotope is 37. So that's an important thing to, what I do. Screen sharing is stopped. I didn't mean to do that. I meant to just go to the, okay, you should still see it. So important thing to know is that the mass number equals the protons plus the neutrons. Important. Okay, so I should do the screen sharing to screen 2 now. Okay, so any questions on that? No? Okay, so here's a trick question. Now, carbon has 3 isotopes. There's carbon 12, which is the most abundant. There's carbon 13, and there's carbon 14. Carbon happens to have an average atomic mass of 12.011. So that's the number it would say on the periodic table for carbon. What percent of carbon atoms have an atomic weight of exactly 12.011? The heading of the question may tell you the answer. Anybody want to guess?
None.
Good. None, 0%. Awesome. Yeah, none. Because the average atomic mass is exactly that. It is an average of them. So when we're dealing with number of atoms, we are in the 10 to the 22nd, 10 to the 23rd range when we're dealing with moles. So that's what we're going to learn about Avogadro's number. It's pretty soon. So that range is huge. That number we can't comprehend. I'll try to give you comparisons later on so we can try to comprehend it, but it is so massive we can't comprehend it. Therefore, any sample that we can tangibly hold of carbon will be an equal distribution of all isotopes. So we have, in terms of, based on their abundance percentages. So for carbon 12, it's 98%, carbon 13 is like 1%, carbon 14 is like 0.04%. So every sample, if I take a carbon sample from here, it will have exactly those ratios of carbon 12 to 13 to 14, because we're taking so many atoms that they will equal out the number of the isotopic abundance will equal out no matter what sample we take. So that's why we have to use the average atomic mass when we're dealing with samples in a reaction that we're using for an experiment. So there's only 3 types of carbon. There's no such thing as carbon 12.011. There's carbon 12, 13, and 14. So none. Good. Okay. So we already tickled this this topic already, but the components of the atom, very important to understand. You have the protons, which are positively charged, And I suggest you write this down just to have the really key information in your notes. So protons, they have a positive charge, +1. They're located in the nucleus, and they have a mass of 1 atomic mass unit, approximately. So if my mass spec professor for one of my graduate classes saw me give this lecture, he would cringe, because technically it's 1.0078, and the neutron is 1.008 something, but they're approximately 1. So then that brings me to the neutron. The neutron's located in the nucleus. It's neutrally charged, and it's very important. And I'll ask you a question in a second, but it has a mass of 1 approximately. So here's a speculative question as you're writing that down. Why do you think neutrons exist? They're in the nucleus. They don't have a charge, right? So they can't be helping to pull or push anything towards each other in reactions. And also, all isotopes of an atom, they act exactly the same in chemical reactions. Whether it has more or less neutrons, it doesn't affect the reactivity of it. So why do you think, if that's the case, why do you think neutrons exist? Or what's their purpose? Any ideas? No ideas?
Doesn't it have something to do with the fact that like the protons and the electrons would attract each other since they're opposite charges?
Yes, that is very close. Good. So it has to do with charge. Not exactly the answer, but very close enough. No one else really said anything. But so thank you for answering it. Now it has to do with charge. So you're on the ball. Now the nucleus is very small and very dense, and it has all of the mass of the atom inside of it, all the protons and neutrons. Now, if those protons are in close contact with each other and they're positively charged, what is that going to mean? They're going to they're moving too. So they're going to bump into each other. They bump into each other. They're both positively charged. What the hell is going to happen? They're going to repel, right? They're going to repel at a faster speed when they collide, because if you do that with magnets with two positive ends, they repel each other. So that will happen. And then it will happen again. And it'll happen again. And it'll happen millions of times a second until the kinetic energy of the protons hitting against each other will become so great that it will break the nuclear force barrier. The nuclear force barrier is the force that is holding the nucleus together. And when that happens, you have radioactivity. So neutrons are technically, we can call them buffers. They are buffering the proton interaction and preventing it from going radioactive or being unstable. So neutrons are very important. We would all be dead without neutrons. So, or electrons or protons, we'd all be dead. So good to know. All right, any questions on that? No? All right, so then we have the third subatomic particle, which is the electron. Electron is negatively charged, and it is around the nucleus, not inside. And the positions of the electrons vary between energy levels. And we'll learn about this in chapters 8 and 9. We dedicate 2 chapters to understanding the position and the energetics of electrons. So electrons, basically for now, their mass is very small, and they're located around the nucleus. They have different energy states and energy levels. And they react. So there's different types of electrons. There's valence electrons, which are the ones that are the furthest away from the nucleus, and they're the ones that are the most reactive, and they are exchanged, or there's interactions with them in any chemical reaction. And then there's internal electrons, which are also important. And yeah, so so the mass is very small. So the mass is, so let's say the proton's 1, the neutron's 1, the electron is 0.00055. That is approximately 1/1800.
Omar, what did you get flowers for?
Yeah, me too. So it's pretty small. Now what that means is we can consider it in this class to be negligible. And the reason why is because if it's 1/1800, I think it's 1855 or something, that means it takes 1,800 of them to make one AMU, one of these mass units. Now, the periodic table has 118 elements, so 118 is the biggest one we can deal with in this class. And it has 118 protons, 118 electrons if it's neutral. That means at most we'll be having 118 out of 1,800 of the ratio of mass to make one. We'd have like 10% or 10% of one AMU at the most, is what I'm trying to say. So overall, we can consider them negligible. And then a funny meme or GIF, there's Jimmy Neutron. So that right there, that's an atom. And you see the electrons going around it. Okay, cool. So how do we know any of this? This is not gonna be tested on really, but it's a good technique to be aware of, especially if you're going into chemical engineering or nuclear engineering or even environmental engineering, because it's a good way to really quantify any type of sample you have. And you can actually tell the structure of most samples. So the answer is mass spec. So I actually took a graduate course on mass spec where we learn a lot about the technique. I like to think I learned things, but it was a night class and I was exhausted most of the time. So it was tough. I got an A somehow, pulled it out. But basically what this is, let's just talk about let's show the picture. So mass spec is a technique that is used, it uses a very high magnetic field and a vacuum it does two things. One, you put the sample in, it ionizes the sample. And what that means is it becomes charged. No matter what the sample is, it becomes charged. You put ionizing radiation, or there's different ways to ionize, but let's just say we use ionized radiation and the sample has a charge. So what do they say here? They have the electron. So the sample goes in. Let's take it from the start. Where's my mouse? Here. Oh, good. Okay, cool. So, all right. So the sample goes in. There is the beam of particles. There is so the electron beam ionizes the sample. So it's ionizing radiation. So now at this point, all of the samples now have a charge. Then they go through an electric field, which accelerates them into this magnetic field. So the magnetic field, based on their speed at which they go through, separates them based on masses. So as you can see, the heavier particles are going to not be as bent, the path of the heaviest particles are not going to be as deflected as the lighter particles, because it's a lot harder with the magnetic field, or with really in any logical sense, it's harder to deflect a heavier object moving at a speed compared to a lighter object. So the heavier objects will not deflect as much, and they'll have a different diffraction angle, and that will mean the detector will detect them at a certain point that's different from the lighter particles. This separation is so sensitive that it can separate things based on 1 electron of mass difference. So you'll have, and the way you show the data is like this. I will mute whoever's talking. All right. So this is how you're going to show the data. This is called the mass spec. It's a really shitty mass spectrum. It actually doesn't look like this at all. But just to make it simple, it really has a lot of spikes and noise and stuff. But for all intents and purposes, you're going to have peaks at your different masses based on where on the detector the sample or different atoms were recognized. And you can actually tell the difference between chlorine that is a 2- versus chlorine that's a 1-, meaning they're 1 electron different. You can tell that there would be 2 separate peaks. And if you have a really good mass spectrometer. So very powerful technique. And something else that's worth noting, I think there might be a homework question on it when we're dealing with these kind of things. Relative abundance. So relative abundance doesn't mean the amount. Doesn't mean amount. So it doesn't mean there's 75 particles of, well, in this case it's instead of 100, but it means it's percent. It's all based on percent abundance. So keep that in mind as you're doing homework. I think there might be a question on it. But so chlorine 35, we know it's 75%, and then chlorine 37 is about 25%. Now, this is normally the y-axis. The reason why I say that, normally the y-axis is intensity. And it goes from 0 to 100. So the intensity basically means the percentage. So that's important to note. Okay. So any questions on that so far? No? All right. So let's talk about the mole. So the mole, we'll just cut to the chase. The mole is, oh, the chemist doesn't. So that basically means the mole is a quantity of particles. Could be a mole of people, could be a mole of anything. Doesn't have to be atoms, doesn't have to be molecules. But it is a definition that has a number that represents the definition. And the number is 6.022 times 10 to the 23rd particles. And this is what we call Avogadro's number. So you could say like avocado's number is like a joke. Yeah, classic. It's funny, like from my community college, I taught almost the same lecture this morning. So like, it took the steam out of my jokes because I'm saying it the second time today. But yeah, avocado's number again. All right, here we go. So a mole, a way you can think about a mole is it is an Avogadro's number of particles. That's the best way of a definition. So some people are like, oh, what's a mole? Oh, it's the number of atoms in something. Nope. It is an Avogadro's number of things. It could be anything. And it says it right there, anything in caps. All right. So follow-up questions based on this huge number. So it's 6 and 23 zeros. Do you think that there's a mole of trees on Earth? No? Less? You think there's less or more? Less? Way less. Yeah, exactly. What about insects? No, like ants though. There's a lot of ants. Ants everywhere. No. Okay. All right. Fine. You guys are on the ball. Whatever. You can see where this is going. You're really smart. So, do you think there's a mole of blades of grass on the Earth? No. Yeah, I heard a yes, but the answer is no. So as you can tell, there's a lot of blades of grass. Now, what about grains of sand? It's a good one. Yeah, that's one you could believe. So think about grains of sand on Earth. You go to the beach. That's nothing. I'm talking about like the Sahara Desert is the size of the United States, and it's sand miles deep in sand. The bottoms of the ocean are all sand, and they go miles deep in sand. I'm not sure about miles, but hundreds of feet deep in sand, and it becomes like clay. But and all the beaches, all the oceans, which is 75% of the Earth's surface area, and all of the deserts, which are huge. There's the Gobi Desert, which is massive. So the answer is no. And we will quantify this. Just to give you an idea. Why does it do that? Stop the screen sharing again. All right. So, all right, we will quantify this. I guess I'll write it in the corner. So I'll write it up here. So the approximate number of grains of sand on Earth is 3 times 10 to the 18th. And the way it was somebody's PhD thesis to go around the Earth and count them all. No, it wasn't. But they probably just did that by surface area and extrapolated. But approximately 3 times 10 to the 18th. And it's increasing every day because rocks are being shaved down by water and stuff like that. But it's about 3 times 10 to the 18th. Avogadro's number is 6 times 10 to the 23rd. This means that, ignore the 3 and the 6, or we can factor that in, but roughly there is 10 to the 5th times more, or really we could just make it 2 times 10 to the 5th times more particles in a mole than there are grains of sand on Earth. 2 to the 5th, 2 times 10 to the 5th is 200,000. That doesn't mean there's 200,000 more grains of, or 200,000 more particles in a mole than grains of sand. 200,000 times more. Times. That means, well, one time is we see all the sand on the Earth. If we double that, almost all of the surface of the Earth is covered in sand. If we double it, think about if we triple it, quadruple it, 200,000 times it. That's like, it will encapsulate the Earth thousands of miles deep in sand. It would be 10, 20, 30 times more than the mass of the Earth, maybe hundreds of times more than the mass of the Earth in sand. I wonder if that covers Jupiter. I'm not sure. Well, Jupiter is huge. That's like, Jupiter's what, 1,000 Earths or something? The Earth, the sun is 1,000,000 Earths. But all right, anyway, whatever. Basically, the mole is pretty damn big. So to give you an idea of, that's just, grains of sand are very small. We know that unfathomable number to create a mole. Now let's think about why we're using this number in the first place. I said before that when we talked about law of definite proportions, or law of conservation of all those laws in the beginning, I said that the mass of oxygen, the molar mass of oxygen, is 16 grams per mole. That means an Avogadro's number, the 6 times 10 to the 23rd, atoms of oxygen weighs 16 grams. Fit in your hand, 16 grams. For iron, 55 grams, 55.8 grams. And that could fit in your hand, a little bit heavier, but it could fit in your hand. Now, think about that for a second, of how small these atoms have to be in order for a tangible amount, 50, 20, whatever grams, to fit in your hand. Meanwhile, the same number of grains of sand cannot fit on the Earth 1,000 times. It's so far off for that. You have to fit on Jupiter, maybe. So that's how small atoms are. We can't see individual atoms. So they're actually called atoms are submicroscopic. Like our best, we can detect them, of course, by mass spec, by different types of analytical techniques. And we can detect compounds by a plethora of techniques, but we can't individually see them. Like, oh, there's a picture of an atom. We could just have model representations of them. And we can see what they do, and we can detect their reactions based on energy and other things, light stuff. Yeah. Okay, so that's pretty cool, right? Yeah. All right, cool. All right, moving on. I'm going to switch the screen share to screen 2 so all the online people could see. All right, so the mole, we know what it is already. We did that already, cool. All right, so now the value of the mole, how they got it, is they use carbon as the standard. So carbon, since we are carbon-based organisms, they used carbon-12 as the standard of the mole. And they said this Avogadro's number is the number of atoms that is exactly 1 mole of carbon-12. So that's 12.011 grams of carbon is exactly 1 mole of carbon atoms, which is 6.02 times 10 to the 23rd. And this was extrapolated to figure out the molar masses of every known atom, of every known element. And that's how they figured that out. Any questions? No? Okay, so this mole number could be used as a conversion factor. So we can have 1 mole of atoms is equal to 6.02 times 10 to the 23rd atoms, or the other way around, just like we've done last class when we dealt with our unit conversions. So let's jump into it. So I'll give you guys, I've been talking for a bit, I'll give you guys a couple minutes to figure this out. So how many molecules are in 2.35 moles of HCl? So the first one, anybody want to volunteer on just how they did it? Well, what kind of math did you set up? Yeah. Okay, good. So 2.35 times Avogadro's number. Good, because you know that 1 mole is Avogadro's number. So 2.35 moles is 2.35 times Avogadro's number. And you notice it doesn't matter that it's HCl. It doesn't matter. It could be H2O, and the answer is the same. It doesn't matter what compound it is, because the number of moles or number of Avogadro's, the number of particles in Avogadro's number doesn't change. Then doesn't matter what compound you're using. So that's that. What about the second one? Anybody want to volunteer? You want to do it again? Yeah, sure. Perfect. All right. So for how many moles are in that many particles, you know that Avogadro's number again is the 6.02 times 10 to the 23rd. So you're going to take that number and divide it by Avogadro's number, and you're going to get some percentage of a mole. And those answers are right there. So for the first one, it would be 1.41 times 10 to the 24th. Now, well, if you're doing it by hand and not doing proper scientific notation, you might get 14.1 times 10 to the 23rd. Also a correct answer. I'm not going to be a stickler for scientific notation, but on the exam, since the exam is completely on Canvas, they may only accept it in proper scientific notation. So if you need to go back and to check how to do proper scientific notation, go ahead and do that. And then the second one, you just divide, like I said, and you get 0.71. Okay, any questions on this? No? Okay, moving on. All right, so the molar mass. We are going to learn the molar mass of everything right now. So in the next 2 slides, you'll know how to do the molar mass of any compound to ever exist. So the molar mass is, we talked about where to find it on the periodic table. It's the decimal number, and it's on the bottom underneath the symbol. And basically, it's the amount of the grams in 1 mole. So if you look at aluminum, 2.98 grams in 1 mole of aluminum. That's Avogadro's number of atoms of aluminum. So that's pretty straightforward, and we kind of looked at that already. So what I want to do is we can do the first one. What is the molar mass of carbon? 12.01. You take a look at the periodic table and you see that it has 12.01 underneath it. That means it's the average atomic mass, the molar mass. So average atomic mass and molar mass are the same thing. So what I'm going to do is I'm going to quit that and okay. So, oh no, that's the answers. Oh, damn it. Ta-da! All right, good job, guys. I'll do it with the pen. All right, so the first question is, what is the mass of 0.67 moles of carbon? So we know the mass of 1 mole of carbon is 12.01 grams per mole. So now, what is the mass of 0.67 moles? Multiply that by 0.67 moles. The moles will cancel out, and you get 8.04, or if you want to do proper sig figs, 8.0 grams. So yeah, that's how you do that. In terms of periodic table, now when you're doing your homework for this chapter, you can have a periodic table online. And what I'm going to do is I'm going to put a link in the chapter 2 module of a interactive periodic table. You can just look up, I think it's called ptable.com or .org or something. And it gives you a really good interactive periodic table. You can click on it, see the different properties of things, all the masses and the numbers, electron configuration when we get to that. So it's very helpful, but it's good to have that on hand when you're doing the homework because you're going to need it. And on the test, you will have it, so don't worry about that. Okay, so how many moles are in 45.67 grams? So we'll write down our measured number, 45.67 grams of carbon. If we know that 1 mole is 12.01 grams of carbon, our grams will cancel out, and we get 45.67 divided by 12, 3.803 with proper sig figs. Okay, so I'll put this back up on the screen. Okay, so is there any questions on that? No? Okay. Weird timing, all right. All right, so this is important. This slide is very important. Now, this is an overview of how to do every type of molar calculation. So on the left here, well, let's look at the middle. So you're gonna have problems where you're converting between moles, between the grams of your sample, and between the number of atoms or molecules. And there are 2 key conversion factors which we both used, which are Avogadro's number, which when we're dealing with converting from or to atoms or molecules, and you have the molecular weight or the average atomic mass or the molar mass. So those 3 terms I just said are the same thing. Atomic weight, molecular weight, average atomic mass, molar mass, fourth thing. For our intents and purposes, they're the same thing. And depending on which source you're looking at, reading a book, looking at different YouTube videos, they use them interchangeably. So we're going to be using that as a conversion factor as well. And we're going to be doing them different kinds of, and we can use them in combination, just like we did for converting different units from like in two steps or more. The same thing could apply with molar calculations. And the important thing that I write here is remember to make smart calculations. And what I mean is, so I don't think I'm too smart. So what I mean by that is I like to think of things in the simplest terms of, if I'm trying to solve a problem, what is my answer going to look like? What is the answer going to be like? Is it going to be a big number? Is it going to be a small number? Is it going to be bigger than the starting number or smaller? This is what I mean by smart calculations. If your number, let's say you're doing how many atoms are in 3 moles of something, and you get your answer as 7. That's not the answer. Because, oh, number of atoms, your brain should automatically think, gotta be huge, gotta be huge, gotta be 10 to the 20 something. So if you get 12 or even 10 to the 12th, you could think, all right, that's really, really small. It should be somewhere in the 20s. So that's what I mean by smart calculations. When we're going from moles to grams, moles is usually a very small number. In this class, you're not going to see moles in the hundreds. You're going to see moles would be point something or 1 or 2 or 5, right? But it's never going to be 4,000 moles. Grams are going to be a lot bigger. They may be 10, 20, 0.1, could be 100, could be 200, but they're not going to be a million. It's not going to be 10 to 23rd. That's for atom number. So make sure the numbers you get for your answers make sense with what you're trying to figure out and make sense for the unit that they're in. So that's what I mean by smart calculation. Now, going into more detail, oh, question. All right, Josh, I appreciate that. All right, Taco Bell pickup. Actually, probably 5 minutes. Okay, so going over these conversions real quick because we're going to do 4 or 5 questions with them and on your own, so you can schedule your Taco Bell pickup when you're doing the questions. So when we're going from moles to grams, we'll do that first. So moles to grams. It's a bigger number. You're getting from a small number to a big number. So what are you going to do? Multiply, right? And you're going to multiply by the molar mass. So it makes sense to multiply, and then like we did on those examples, you're multiplying by the molar mass. So going the other way, going from grams to moles, we're going from a bigger number, let's say 12 grams of carbon, down to the number of moles. So we're going to divide by the molar mass. 12 divided by 12 is 1. Get to a smaller number. Going from the moles to the atoms or molecules, you multiply by Avogadro's number. Moles are very small. Atoms or molecules are very big, 10 to the 23rd. So it makes sense that you have to multiply by your 10 to the 23rd number. Or a big number, the Avogadro's number. Going the other way, you divide. That's basically the conceptual plan. Is there any questions on that? So be smart with the calculations and do the math. Yeah. If you do the math wrong, the number will be way off. So that's an easy way to tell if you're wrong. Okay, cool. So next. Oh, you guys didn't know what I was talking about. So the group chat only comes on this screen. So Josh asked if he wants to schedule his Taco Bell pickup. He wants to know when the break is. So that's funny. Class clown. I was the class clown, but nobody thought it was funny. So I thought I was the class clown. Okay, so we'll do this one together, and then there'll be 5 we can do by ourselves, which will be followed by a break. So find the mass of carbon atoms that has. It's okay. The mass of carbon atoms that has 9.86 times 10 to the 23rd atoms of carbon. So we'll do this one together. So I'm gonna escape from this. That will stop the screen sharing for some reason. Don't know why it does that. Didn't do that last week. Okay. Okay. Oh, poop is the answer. All right. We have the work here. Cool. So what we know that 12.011 grams of carbon is 1 mole of carbon. And also we know that 1 mole of anything is Avogadro's number of the atom or particle. So we have our given number, which is our 9.86 times 10 to the 23rd. And we are going to divide that by Avogadro's number, or multiply it by the ratio. So Avogadro's number, the atom numbers will cancel out, and you'll end up with moles for this middle step. Then we want to go directly from moles to grams. So we're going to use our other conversion factor, which is 12 grams per mole. And then we're going to use that in our unit conversion, and the moles will cancel out, and we will get 9.86 times 10 to the 23rd divided by Avogadro. That gives a little bit more than 1 point something, and then multiply that by the molar mass, which is 12, should give us 19.7. So I'll give you a second to write that down, and then we can do some on our own. Any questions on that? No, you guys are quiet. Bless you. You guys are quiet. Okay. All right. So time to do some on our own. Oh, yeah. So here's another important skill. So what if we don't have just carbon? What if we have a compound? So finding the molar, bless you again. So finding the molar mass of any compound is very important. It's very important to get really good at it so you can do it quickly. Because a lot of the times in these questions when we're dealing with, in this class especially, really every chapter we learn, the math problem, the calculation-based problems, one of the first steps is going to be finding the molar mass. So it's important that you get really good at it, that you're like snappy with it, maybe memorizing. Well, if you practice a lot, you will end up memorizing unintentionally the molar masses of common elements, like oxygen 16. You heard me say carbon 10 times already is 12. Chlorine is 35.45. Sodium is 23. Things like that. So to find the molar mass of a compound, like you have Na2SO4, which is sodium sulfate. I had to think about that for a second. So sodium sulfate, you basically just add up the molar masses of all of the atoms involved in the compound, and you get your answer. So you'd have 2 times your sodium plus your sulfur plus 4 times your oxygen. And all those numbers could be found by looking at the periodic table. So definitely have periodic table on hand when doing the homework and everything else. So the test, you will have it given to you. So add up the molar masses, multiply the number of atoms of each element, and then for sodium sulfate, you get 142. Okay, so does that make sense to everybody? Is there any questions on that? Don't feel like you're asking a dumb question, because if you have the question, I'm sure someone else does as well. Oh, okay. So what we're gonna do is, let me double check. There's my cat. There's my cat. She's adorable. Anyway, so what we're gonna do is we're gonna take our break. It'll be a 10-minute break that has these molar mass questions. So I recommend, so I want to, there's 7 of them, the 7 of them. So these molar mass questions, I want an answer for all of them. I don't have the answers on the slides, and I'm not going to do them. So I want an answer for all of them by not just one person, by anybody. So maybe some of you could do the last couple, 3. You don't have to do all of them, but just maybe some of you could do last 3, the first 3, or the 4, just so one person does at least one each, that I have the answers for them. I explained that really roundabout, but you get what I'm saying. Okay, so we will take a break for 10 minutes until 7:25, and Josh can get his Taco Bell. 25. Okay, so everyone should be coming back now. I guess we'll go right into it. So who can give me the answer for the first one? That's called magnesium nitrate for the molar mass. 148 sounds good to me. 148 grams per mole. It's approximate. And in terms of something I didn't mention is rounding. So on the periodic table, you might see oxygen is 15.99. You can round that to 16. Nitrogen is 14.01. You can round that to 14. Things that you can't round, like chlorine. Chlorine is 35.45. Not good to round that one, because if you have two chlorines, you might be off by a whole unit. So not the best thing. Okay, good. Next one, H3PO4, otherwise known as phosphoric acid. You guys have one job. The second one, H3PO4. It's at least 3, I'll tell you that. Give or take. 98, sounds good to me. 98, good. Grams per mole. All right, next. CH3COOH, otherwise known as acetic acid. Yes. 60.057. So, 052? Okay. So 60.05, fine. It's good, 60. 60 is fine. Because you have the hydrogens are 1, carbons are 12, oxygen 16. So lead, this is actually lead 2 nitrate. So lead PbNO3 2. Yes. Sounds good to me. 331.2 grams per mole. And we didn't go over the parentheses, but basically it's just like the distributive property in math, where you have NO3, you find the mass of that, and then you multiply it by 2. Good job. Next one is ammonium sulfate. NH4,2SO4. Anybody? 114, probably right. Okay, good. Next one is gallium 3 sulfite, Ga2SO3. That one might require a little bit more work. Did everybody get Taco Bell in the break? Is that why you didn't do it? 379.6, good enough. All right, that sounds right to me. It should be pretty big. And then you have this one, so difluoromethane, 120.5, 0.9. Okay, good, awesome. G per MOL. That's sloppy. All right, cool. Good job, everybody. So is there any questions on how we solve these, or do you want me to go over another one or any of that? I think it should be pretty good. You basically just add up all the elements. So, okay, good. All right, so now I'm going to continue. I'm going to make this bigger. All right, so let's do another example of a mole calculation question. So how many molecules are in 46.1 gram sample of barium chloride? So we have a lot going on. We have a compound this time. So instead of just carbon, we need to figure out first the molar mass of the compound. Now, in these kind of questions, even if you get lost and you have a compound formula, a very good first step is to always find the molar mass of that compound. It'll help you. So what we know is we can calculate that, and the molar mass of that compound of barium chloride is 208.23 grams per mole. Okay, so I'm going to ask you guys, what do we do next? What's a good next step? So you have that many, you have a bigger sample, and we have the molar mass. What can we do? Perfect, awesome. So we can divide the gram sample, which by the number, it's bigger than a mole, divide it by the number of grams per mole to get the number of moles in that sample. So the sample divided by the grams per mole of the sample equals the grams of the sample, or the moles of the sample. So it would be more than 1, but let's see what we actually get. So it's 1.0, oh, it's about 1. So 1.001 times 10 to the, oh, that's the molecules. So for that, so what is 346.1 divided by 208.23? All right, about 1.6, whatever. So that number of moles now, we want to convert it into molecules. So who could tell me, how do we go from moles to molecules? Perfect. Multiply by Avogadro's number. Good. And once you do that, you get around 10 times 10 to the 23rd, or 1 times 10 to the 24th. I'll leave that for a second. There's any questions on that? So that's a really good comprehensive problem on everything we learned so far. You got molar mass in there. You have conversion from grams to moles, and conversion from moles to molecules. That's a very good practice question. I'll leave it up for a second. Good. 3, 2, see someone's still right. 3, 2, 1. Kitty. Yeah. Her name is AC. It's spelled ACY. And she's psycho, as you can see in the left picture. But yeah, she's my cat. She's awesome. All right, so now we're gonna learn about the configuration of the periodic table. So you have elements. Oh, there's a comment. It better be on how cute she is. Let me see. Yep, I knew it. Adorable cat. Thank you. I know she is. She's a model. She's awesome. Okay. So in case you're wondering, she is how old? She turned 2 in August. So still a youngster. All right. So elements in periodic table. So we're going to go over the different types of elements. So there are 3 classifications of elements. There are metals, which are actually most elements are metals, believe it or not. Different types of metals, but they are metals. Then there are metalloids, and then there are non-metals. So just from the name, what do you think a metalloid is? Anybody? Yeah. Yeah, it's like a halfway point. Yeah, it's got some characteristics of metals, some characteristics of non-metals, and it's just, they have nowhere else to put it. So that's exactly what it is. Silicon is one of the most popular ones. So, well, I'm going to say one thing first about the periodic table. So the periodic table, it's not perfect. Think of it as this. We are humans, and we tried to find the best way that we can organize things that are naturally occurring that makes sense in a way that makes sense to us. That's what the periodic table is. It's not perfect. There are some cases where once we go over the organization, oh, why is this over here? Because there's nowhere else to put it. That's the answer for a couple of things. So we are trying our best, because our level of intelligence in terms of the information left to be discovered is very low. You know, because the aliens, come on, the aliens have us beat. But so we're not at a high level of organization. We're only like what they call a class 1 civilization. Like so we're trying to find the best ways to represent this to make sense to us. And the periodic table is the best way we can figure out. And there's still flaws. So we'll talk about that once we see the picture of it. So metals, they're on the lower left side / middle of the periodic table. And they have general properties, which you don't have to go crazy on these properties, just maybe know them. So they're good conductors. They're good at conducting heat and electricity, like copper wire, for example. They can be pounded into flat sheets. They're malleable for the most part. Some are more malleable than others. They can be drawn into wires, so just like in the conductivity. They're often shiny. Sometimes they're a little bit more brittle, but often they're pretty strong. And this is an important one. They tend to lose electrons when they undergo chemical changes. So when they are in reactions and when they form ions, they are the ones, the metals, that become cations. That's why I showed you my cat before, cations. So a cation is something that is positively charged. And you can tell by the definition of tends to lose electrons. if you're losing electrons, you're losing negatives, you're gaining positives, basically gaining positive charge. That's what metals do. So metals become positively charged cations when they become charged. So that's a very important, that's probably out of this slide, that's the most important thing, because we're going to be using that to determine all their charges. And then there's some examples: chromium, copper, strontium, whatever. Okay, so you have metals then, or not, sorry, non-metals. So non-metals there's not that many of them. They're on the upper right-hand corner of the periodic table. They include the noble gases, they include the halogens, they include some other elements that are in there. There's not many of them. There's only 17. And the metals, I don't know how many metals there are. It's probably 80 something, 90 something. So they tend to have these properties. They're poor conductors. They're usually brittle. They're usually powder at room temperature, like sulfur, phosphorus. They form a powder. They're the opposite of metals in their way of reacting in chemical reactions. They tend to gain electrons. And we'll talk about that more specifically when we talk about cations and anions, but there's a reason why they like to gain electrons. And I'll talk about that soon. And there's 17 of them total. 5 of them are solid at room temperature. You have carbon, phosphorus, sulfur, selenium, and iodine. Those tend to form, like iodine are crystals, they're purple crystals, but the other ones are just dust, like powder. And carbon could be graphite, could be diamond, and those occur at room temperature, graphene. So those are just some examples. And phosphorus, sulfur, and selenium I know are just like brittle powder material. And one is at room temperature. One at room temperature is a liquid, which is bromine. I was about to say bromium. Bromine. Bromium is not a thing. So there are 11 that are gases. Most of them are gases. And this is where a lot of them occur as diatomic gases. So the gas ones, you can read that list off. But the important thing is to be familiar with the ones that are diatomic gases, meaning they diatomic 2 atoms. So they have 2 atoms when they form in their molecular state, when they become molecules. So you have hydrogen, you have oxygen, you have fluorine, bromine, iodine, nitrogen, and chlorine. I feel like there's one missing. No, that's it. Yeah, those are them. So those are the diatomic gases. You can write those down. That'll help. Any questions on that? No? Okay. Boop. All right. Metalloids. So metalloids, I never heard them. No one's ever called them semi-metals before. That's stupid. But they lie along the zigzag diagonal line, which we'll see on the periodic table, and they have mixed properties, and they're mainly used for semiconductors. So whereas metals are full conductors, meaning you can't really modulate the voltage through a metal. I mean, you can't modulate the electron flow, the current, not the voltage, the current. So it's either on or it's off. Bless you. So you can't change the level of current because they're too strong of conductors. Semiconductors like germanium, and silicon, for example, they have very good semiconductor properties, meaning the amount of current that goes through them can be regulated. And this is how computers became a thing, because we can have silicon chips that we can change and regulate their voltages, their current that goes through them to get different signals. So they're very important. Okay, so let's just go here. All right, so this is the periodic table. We're missing the bottom chunk. I don't know why this picture even exists then if it's missing the bottom chunk, but we can take a look at what we got here. So there are, I know why this is here, to tell you about main group. So there are 2 different groups of elements. There are what we call the main group, or the A group, and then the B group, which is the transition elements. The A group are the ones in yellow, and my cursor on the main screen. There it is. All right. So the main group ones are on the left and on the right here. They're higher. So you see they're higher up. Now, we have group numbers for the main group elements. 1A, 2A, 3A, all the way through 8A. And those numbers are very important to know. So you see how hydrogen is group 1A, Beryllium is 2A. We skip the entire middle section. And then we go to boron, which is 3A, and so forth. That's important because those numbers can tell us a lot about their ionic charge when they become ions. For example, the group 1A elements, when they become ions, all of their charges become +1. Very easy to remember. If you remember this pattern, it's pretty easy. So group 1A becomes +1. Group 2A becomes +2. Wow. Didn't see that one coming. But this one's tough. Group 3A, oh, +3. Not quite. So group 3A, aluminum is +3 all the time. Boron is a metalloid. It doesn't really follow the gaining or the losing electron pattern of metals. So it really doesn't, we don't really, such a varying charge that we don't know. It usually takes place in not ionic bonds, but covalent bonds. Then everything underneath, you have gallium, indium, whatever that is, thallium or something. Yeah, so those, they are transition elements as well. We call them post-transition elements. What that means, really, is they are transition metals, but they had nowhere else to put them. So they go there. They're post-transition elements. So they follow the same exact properties as transition metals. And we'll learn about that. That comes into play in chapter 3 and 4 when we talk about naming, which will be next week, I think. I lose track, but it's coming up soon. Not this chapter, though. Okay, so then, yeah. So then for 4A, 5A, 6A, and 7A, the best way we can do it is describe it from the other way. So 8A, we'll go backwards now. So 8A, these are called the noble gases. They are noble. See, noble gases. They are noble. And what this means is that they don't like to react with anything. And the way I like to think of them is like they look like they're no nonsense molecules, right? They're just like, they're very intellectual, right? They don't like to argue on Facebook with people. They're very non-reactive. So I like another example is like like the London guards, the royal guards in London with the funny hats. So like there's videos of like people online going up to them and like pretending to hit them or like doing stupid stuff, taking selfies with them or whatever, and they just stand there. They don't move at all. So they are noble knights for the queen. Same concept. They don't like to react with anything. The noble gases don't like to react with anything, and they're called inert gases as well. So those are the noble gases. Now these noble gases do not have a charge because, oh, that makes sense, because they're noble. They don't like to react with anything. Anything with a charge tends to react with things with the opposite charge. So they don't have a charge. But then once we go backwards to 7A, just get my cursor out. Where is it? Right there. 7A, we get to the halogens. These halogens they have a -1 charge. So you saw that group 1A has +1. And also there will be a chart summarizing all these charges I'm saying. You don't have to like frantically write them down. So I'm just getting you familiar with the terminology. So 7A, they're going to have a -1 charge because they are the noble gases with one more, or with one less electron than they need. So they're kind of like, to get to a noble gas, they need they need to get rid of one electron, or they need to, gain one electron. Yes. So yeah, so that's what they need to, the halogen, need to gain one electron to get to a noble gas configuration. Noble gas configuration is when they're kind of happy. And when it gains one electron, it becomes +1. The oxygens need to gain 2 electrons when they form an ion to have a noble gas configuration. Therefore, since oxygen only has at a ground state or at a neutral charge, so it has 8 protons, 8 electrons. So when I say neutral, I mean the protons and the electrons are the same. So the atomic number is 8 for oxygen, therefore it has 8 protons and 8 electrons. From that state, from that neutral state, it gains 2 more to become happy. noble gas configuration is considered happy. So it goes from, it kind of, you can count it. So, where am I going? Right there. So oxygen minus, so it's right here. To gain enough electrons to become a noble gas or happy, you can go, oh no, you can see goes 1, 2. So once it gains those 2 electrons, its charge becomes -2. And then nitrogen and phosphorus actually become -3. So they'd have to gain 1, 2, 3 electrons to get to neon, or to get to the noble gas. So there'll be a chart, I think, later on showing the charges, and I can explain it again. But hopefully conceptually that makes sense. And then you can, a good question could be, oh, what about the middle ones? What's their charge? It varies. So they're called transition metals for a reason, because their state of ionization always changes. It could be, in one compound, it could be -2, or not minus, +2. One compound, it could be +1 or +3, or even as high as +6 or 7. Okay, so we talked about noble gases already. Then we have the alkali metals. So the alkali metals are in group 1A. They consist of all those listed, and they explode violently when reacted with water. Important to know. Why? Because in case you want to explode something violently with water, you know, get some sodium metal, or some lithium metal, or some potassium. And this doesn't mean like, oh, I can get NaCl then, right? It has sodium in it. Why doesn't it explode when I make salt water? Because that's a different compound. So sodium chloride is completely different than just sodium metal. Sodium metal is this like, it's right there. It's like a silvery like block of, and it's kind of brittle actually. Like you can, if you hit it, it would fragment. But if you pour water on it, it'll explode. So yeah. Okay, then you have the alkaline earth metals. Similar name, but these are group 2. You can think about it, group 1 has a simple name, alkali metals. Group 2 has the longer name, alkaline earth metals. Not as reactive as the group 1A metals, but they still like to lose their electrons pretty readily. Then you have the halogens. And you're wondering, we're skipping the whole middle section because these are the only groups that are mainly important. So the halogens, they're 7A, they're very reactive. The reason why they're very reactive is because they are 1 electron away from getting to their noble gas configuration. They're running a race and they're very close to the end, so they're going to sprint because they're tired as hell and they want to get to the end and stop. So they tend to react, and they tend to take in electrons whenever they can. So they have a very high electron affinity, is what we call it. So yeah, and they're found mostly in salt form in nature or gas. So in salt form, they would have like NaCl, for example. Sodium fluoride is a gas, sodium bromide, but potassium chloride is for road salt. So yeah. Okay, so ions. Now, just to reiterate again, when you have a neutral atom, it means that the protons and the electrons are equal. When there's a chemical change that occurs, that an ionic bond is formed. So we'll talk about ionic and covalent next week. But when we have a reaction where an ionic bond occurs, you have ions formed, meaning there's something with a charge. Ionization means it gives a charge. Ion, charge. Positively charged ions. So you can write in your notes positively charged metal ions, because in our class there's no such thing as a non-metal cation, a non-metal positive ion. We call them cations. So cats are positive because I like cats. Cats are positive. Then you have negative ions. So negative ion is called the anion. So think anti, against. So that is called anion. So they're negative. So yeah, the key phrase are actually the last 2 bullet points. Metals lose electron to become positively charged. Non-metals gain electrons to become negatively charged. That sums it up right there. That's a very good thing, because the non-metals are so, hold on, I'll show you the next slide. But does that make sense? Yeah. All right, I'll give you a second to write it down. moving on. All right, so this shot of the periodic table shows all of the charges that you guys need to be familiar with and know, really. So memorize this chart, but it's very easy to memorize because there's trends and there's patterns. So I will go over it again. Don't really worry about tellurium down here or selenium. I mean, it follows a trend, but I've seen them in different states before. It's fine. Hopefully. So group 1A, 1 plus 1. Group 2A, plus 2. Group 3A, it's actually, you know, every textbook has it different. It's actually aluminum and gallium that have plus 3. So gallium is right underneath aluminum. That also has plus 3 all the time. So then you have the halogens. Hydrogen is here. Why is hydrogen there? Because it could be ignore that. Ignore the hydrogen being there. Fluorine is the first one, and then it goes down in minus. So when we deal with acids and bases, we'll be talking about hydrogen, the hydrogen ion, and that's going to be H plus. H minus is also a thing, but we're not going to talk about it in this class. So you have fluorine, chlorine, bromine, and iodine is -1. Then you have group 6A, which is -2. And then group 5A, actually it's nitrogen and phosphorus, which are -3. So all in all, this is what you would need to know. Yeah, and beryllium is not here because beryllium actually likes to partake in covalent bonds. Why? Because sometimes it does. Yeah, it's weird, right? Because once we learn more about the periodic table, the more you're going to hate it. Because it's like, yeah, this works perfectly. Nah, this one's weird. Good. This one's weird. And there's a lot of exceptions. But this is because, like I mentioned, human beings made this table to the best of our ability to organize these things so that it's easy for us to interpret. But it doesn't mean it's perfect. There's actually a lot of exceptions. So does that make sense conceptually? Okay, so those charges be familiar with. And the reason why those charges exist is, like I mentioned, we want to reach a noble gas configuration of electrons. So I talked about how that applies to the halogens and then the 6A elements and also the 5A elements with they gain the number of electrons required to get to the noble gas configuration. But it also applies to the metals that are losing electrons to get to that configuration. So if you look at group 1A, they have, let's say they're neutral. They want to get to noble gas configuration. They need to lose an electron to get there because it's much easier for lithium to lose 1 electron and end up back here, or back here where right there where helium is, than to gain 1, 2, 3, 4, 5, 6, 7 electrons to get to the next noble gas. Much easier for it to lose 1 than to gain 7 energetically. So that is why metals lose electrons. So maybe in high school you learned they lose electrons and they have charges. But the reason why is because they want to reach that noble gas configuration, and the number of valence electrons that metals have is usually, was pretty much all the time less than 4. It's usually 1, 2, or 3. Since it's 1, 2, or 3, it's much easier to lose 1, 2, or 3 electrons than to gain the remainder to get to 8, than to gain 5 or 6 or 7. That's why they like to lose electrons. And so if you look at 2A magnesium, it's much easier for magnesium to lose 1 electron to get to sodium, lose another electron to get over here. Oh, sorry, the cursor is not on the screen. Where is it? I saw it. Wait, it's on the screen. There we go. Okay, so it's much easier for magnesium to lose 1 electron. It'll be just like the same configuration as sodium. Then it loses another electron. It ends up over here. So it's much easier to happen than if it gains 1 to get to here, then 2, 3, 4, 5, 6. It's much easier to do. Okay, does that make sense? Yeah? Okay, cool. All right, moving on. So think about it now. Don't think about it. Too late to think about it. All right, elements. we talked about that already. Atomic number we talked about. Mass number we talked about. So this is a little different. Kind of a review, but going a little bit more in depth of what we talked about in the beginning of the class. So we know what isotopes are. There is a different type of symbol for isotopes. And this symbol is called the nuclear symbol. The nuclear symbol, because it is specific to each nucleus, meaning each isotopic nucleus. So here's how it's written. You have the chemical symbol is where X is. The mass number is on the top this time. Normally on the periodic table, we're used to the mass number being, or we're not used to a mass number at all. We're used to the average atomic mass being on the bottom. In this case, the mass number, which we went over before, is also listed right on the top, where it's listed as A, as the number of protons plus the number of neutrons. That's the mass number. So that mass number is on the top, and it is all the time a whole number. It's different than the atomic mass. Atomic mass is the average atomic mass for an element. The mass number is the mass that is specific to an isotope, whether it's neon 20, neon 21, or neon 22. And there are questions. Let me see. Oh, good. Okay, yeah. How? Good question. So yeah, I beat you to it. So is mass number different than atomic mass? Yes. So mass number is isotopic specific. So that's why you can have different mass numbers for the same element, but you cannot have different atomic masses for the same element because it's the average atomic mass of all of the isotopes based on their abundance. Then you have Z is the atomic number, which is on the bottom this time. So keep that in mind. This is a different symbol. The notation is called the nuclear symbol and is not to be confused with the periodic table symbol. Okay, and something that makes it really easy to understand is why we make this nuclear symbol. I'm gonna do this. I'll show you. Okay. So I'll draw the neon one over here. I'll draw neon 21 up on the top. So this is neon 21. So the 21 is the mass number, put mass, and then the 10 is the proton number. How do we get the neutrons? Subtract, and look how it's set up. We could just do that. Wow, magic. And we end up with 11 neutrons. So I'm not saying that's the reason why they set it up this way, but it makes it a lot easier to find the number of neutrons. So keep that in mind. Maybe that'll help you remember or distinguish between the two. So, okay, good. All right. Okay, so I gotta switch the sharing to the bigger screen. Okay, cool. Okay, now moving on. So what is the atomic number, Z, and the number of neutrons of carbon-12? So there's a nuclear symbol for carbon-12. What is the atomic number of carbon-12? Anybody? 6, right. What's the atomic number for carbon-13? Yeah, so every carbon isotope has an atomic number of 6. What is the number of neutrons of carbon-12? 6, because the 12 represents the mass number. So the mass number minus the protons is going to be the neutron number. So it would be 6. Good. Now, same thing for nitrogen 14. So what is the atomic number of nitrogen 14? 7. What is the mass number? 14, right, because it's written there. Good. All right, so there's a periodic table again. Something we didn't cover is the organization of groups or of vertical columns and horizontal rows. So the groups are the vertical columns. They're called groups. That's why we call it group 1A, group 2A, group 3A. Then the periods go across. And there really isn't much in common with periods, honestly. Like if you say, what does everything in period 4 have in common? Nothing. There's nothing that they have in common. So if you go through it, you're crossing through potassium, which is an alkali metal, then calcium, which is an alkaline earth metal, bunch of transition metals, some metalloids, and some nonmetals and noble gases. They have all nothing in common. The only thing they have in common is that they increase by 1 proton every element that you go. That's it, because they all go in number order. So that's why we don't really talk about periods in this class, but definitely we talk about groups, because they have all the same chemical properties as the other elements in the same group. Isotopes, we beat this dead horse already. Sorry, dead horse. Okay, so periodic law, that's stupid, honestly. There's no point. So that was the first periodic table. They didn't really know much. Yeah, it didn't look like that at all. It actually looked terrible. They had like more numbers on it, and it was just ugly. But yeah, it was like really spaced out, and it didn't have boxes. It had like lines underneath, and it was just like it was a mess. I have a picture of it somewhere. In a lecture I gave this morning to my class in the community college, I had a picture on the slide. Yeah, this guy Mendeleev in 18 whatever, I don't know what year. Okay, so we talked about this already. We're kind of almost done. I think we are done. The rest of it's just kind of a review. So this is the periodic table again. Oh, experiments. This is good. Yes. So this is the last bit of information. So yeah, so something else that's important is how do we know about all this stuff? So we've known, like, to us, even growing up in like middle school and high school, we knew that, oh, they know about atoms, they know about molecules and like protons and stuff. Maybe we heard these terms thrown around, but how did they discover these things? In the early 1900s, they discovered a lot of protons, neutrons, and electrons. How did they do that? So these are the experiments. I'm going to go over 3 key experiments. 4, 3, I think it's 3, that go over how they did it. So first is the discovery of the electron. Now, J.J. Thomson, back in, I'm not sure what year he did it, but he was alive in the early 1900s, or 18 to 19, wow, that's a long time. 1856 to 1940. Damn, that's a life expectancy back then was like 60 maybe. He lived for like 80 something years. 85, yeah. Yeah, damn. Okay, so good for him. So he did a cathode ray tube experiment. So a cathode ray, we know now, is a beam of electrons. But they didn't know what the hell it was. They just know, oh, if you put these things together, we get a beam. What's in the beam? Whatever's in the beam could help us to determine what's in every atom. So they did many experiments, but here's one experiment they did. They shot the beam through like an electrical field. So they put a positive plate on the top, a negative plate on the bottom, and they saw if the beam bent at all or deflected or whatever, bent, sure. And they saw that it bent towards the positive end. This means that, oh, there's got to be something negative in the beam. So they called that the electron. Very basic experiment, but it worked, and they determined the electron. So they determined that the electrons travel in straight lines, that they are independent of the composition of the material, meaning they're in everything, and they have a negative charge, bless you. So that's what they figured out about the electron. All right, so we got that on the table, good. So now we want to know more about the electron. So this guy Millikan, so I used to, when I learned his freshman year of college, for me, I used to call it Milkman, the Milkman's oil drop experiment. So Millikan, he had this really complicated experiment where he put particles in an atomizer, which is basically just exposing them to high energy to make them into their atomic form, and he put them into a chamber. So this, I'll get the cursor up there. So you have a middle chamber. So you have this, you put them in a chamber, and there's actually, it's not shown here, but there's a slit that the atoms will go through. And then they will go through based on, like, they would be pressurized. So they'd go through here. And then once they're in the main chamber, they would be ionized by ionizing radiation, very similar to how the mass spec works, by shooting high energy particles to knock off electrons in order to make them ionized. So once they're ionized, you notice that they're in between a negatively charged and a positively charged plate. What would happen is the charged droplets will hover, or they'll be suspended in the middle of the electric field based on 2 things. the attraction and repulsion of the atom, the ionized atoms, to the positive and negative plate, and also by gravity. So based on those two forces, they can calculate, and then based on how close the atoms were to the positive or negative plate, counting into the, or taking into account the effect of gravity on top of that, they could actually calculate the charge strength of the electron. So let's say they used helium. Helium would have 2 electrons. Let's say it gets ionized, it has 1 electron. And that means it would be positive. If it's positive, that means it would hover more towards the negative source. So that 1 electron, put that into an equation factoring in gravity, and you would get a charge number for that 1 electron. If it was 2 electrons, you can get a charge number that's probably greater divided by 2. So they figured that out, and they got these numbers. From that, they determined the charge and the mass based on the gravitational forces of the electron. Yeah, but like they flipped it probably. Like in this case, you can ionize things both ways. You can make them positive and negative. But you're right. That's a good point. So you could easily have the same experiment but flip it to figure out the opposite. Okay, so they figured out the electron. These numbers aren't too important for this class, but if you're taking, well, when you take electricity and magnetism, so that's physics 2, right? It's still physics 2 in this school. Are you guys in physics, like mechanics? Mechanics is physics 2? I don't know. In Stevens, you take mechanics first, then you take E&M, but maybe it's switched. I don't know. I hated E&M. That was my least favorite class of all time. I hated it. But basically, you're going to be using these constants a lot: the mass of an electron and the charge of an electron. So yeah. Okay. So Thomson's plum pudding model. This is stupid, but he had an idea that was revolutionary. He's like, all right, if we have all these subatomic particles that we know about, we have electrons, we know their charges and masses, we know that there's other stuff in there, because they can figure out what's the mass of the whole sample, and then the mass of an electron is very, very small, so there's got to be more things in there. But they didn't know what these things were. They didn't know that protons and neutrons were different yet. But they knew that more things existed other than the electron. So they're like, all right, it's got to be some kind of plum pudding model, whatever that means. It sounds disgusting, a plum pudding. But basically that the electrons are floating around this sphere of positive energy, and it's just a blob, a solid blob of subatomic particles, a soup, a solid soup, I guess a pudding. So I guess that makes sense. So yeah, so there's a way you can test this. So this guy Rutherford, they actually named Rutherford after him. I don't know. I made like Rutherford, New Jersey. I just made that up. I have no idea if they did. But you would have believed me. You would have went home. Hey, mom, like I know where they named Rutherford, New Jersey from. No, I don't know. But there's probably other famous people named Rutherford. But anyway, regardless. So he did this really revolutionary experiment. So I'll explain it I'll put the cursor up on the board. There we go. All right. So he got a beam of lead atoms. Right. So this is a brick of lead. Or no, a beam of radiation. Oh, sorry, it's actually helium. So you got a beam of helium, ionized helium, like really high energy. So helium particles are alpha particles. So we'll learn about that when we get to radiation. But he took high energy alpha particles, and the reason why it's surrounded by lead is so they don't get spread out, like they don't hurt you. Alpha particles don't hurt you anyway, but just so we can direct it into one place. So they took this beam and they shot it through a gold foil. So the gold foil is literally just that. It's like aluminum foil, but gold. So it's more expensive aluminum foil. And then they have a detector that goes almost 360 around it. So what they expected, and a picture that the beam is traveling in like a laser, very, very straight line. Now, what do you think? I mean, this shows what happened, but the hypothesis before the experiment started was, all right, you're going to have this beam, because the plum pudding model was the leading explanation at the time. Since the whole thing is the gold foil is solid and they're interlocked, or they're very close together gold atoms, the beam is going to bounce off of the gold foil and bounce all the way back to the detector over here and back to the sphere. So the detector probably won't detect anything because everything will come back to the source. But the opposite happened. So to the data, over 98% of the alpha particles went straight through. Straight through. About 2% were deflected by large angles, but went through. Still went through, but they were deflected. About 0.01% of the particles bounced off gold foil. 0.01, that's 1 in every 10,000 bounce back. So what does this mean? This means that 98% of the space in that gold foil is empty. How could that be? We could see it and we can't see through it. Well, that's another example of how humans are stupid and we are limited by our organs. We're limited by how well our eyes can see and convert the information that they get, convert the photons into reality. That's a very limiting thing. So by that concept, 98% of all things that we see is empty space. Yep. Well, I'm touching it. It can't be empty. It is, because your hand is empty too. But the atoms are so close together that even with that 98% empty space, it is considered solid to us. Because they're so, you know how small, I went over it already, how small and how small they are. So yeah. So this means that, let's talk about those other 2%, the 2% and the 0.01% that actually deflected or hit off of something. That something, what is that something? Nucleus, good. The nucleus is a very, very small, dense thing in the middle. And this is the nucleus. So somewhere between it would actually be somewhere between 0.01% and 2% of the size of the atom is the nucleus. So to get this into perspective, if you take Yankee Stadium, right, and you put a penny of Yankee Stadium in the pitcher's mound, on the pitcher's mound, there's a penny, and you take all of the mass of Yankee Stadium and you put it into that penny, all the mass, that's thousands of tons of steel and concrete. That is the atom, and the rest of it is empty space. All of the mass is located in that very, very small, dense particle in the middle. That's why atoms stay together, because they have an extreme force pulling it in together, that extremely dense particle in the middle, that nucleus. So this stuff's crazy, right? Chemistry just got real today. Okay, so is there any questions on that? So his conclusions were that atoms are mostly empty space because most of them went through. Atoms contain dense particles that are in small volumes. Wait, that was small in volume compared to the atom, but large in mass, which is the very small, dense nucleus. And the dense particles were positively charged because of the deflection angles. And they figured that out as well. So that means he was like, all right, no more plum pudding, you're wrong. Oh, I didn't expect that. All right, so it went straight through. Okay, we get it. Oh shit, again. All right, I think I might do it again. Okay. Oh, 2. Oh. That's weird. Oh, I know why I didn't expect it, because last year when I did this lecture, the room had a VGA cable, so sound couldn't be put through that. But now I'm at HDMI, so that's why. Okay, so the plum pudding model, you would either expect them to all go straight through, or if it was solid, you expect them to all bounce back. There wouldn't be a differential. But in the nuclear model, they all went through. Or most of them went through, and Only a very, very small percent bounce back. And that's how you discovered. So Rutherford discovered the nucleus. He discovered the nucleus was positive, meaning the existence of protons. And then by process of elimination, they discovered the existence of neutrons, because they figured out that, all right, there's got to be, to add up the protons, add up the electrons, there's still some mass that's missing. And if it's missing, it's got to be in the nucleus, because we already accounted for the mass everywhere else. So it's got to be in the nucleus. So then by process of elimination, they found the neutron. Okay, so that's basically the same thing. Structure, okay, we talked about this already. Oh, fun fact. The mass of the neutron is more than the mass of the proton and electron combined. Weird fact, but it's true. Yeah, you would think that the neutron and proton are the same size, the same mass. They're about 1 AMU. But that difference, that small difference, that 1.007 whatever of the proton and the 1.008 whatever of the neutron, that difference is more than the difference of the electron, or than the mass of the electron. So that's a cool fact. What else? Oh, how did he know that most of the particles went through? Good question. Because he had detectors on different sides of the experiment. Here. So he had a almost 360-degree detector that detected the energy and detected the amount of particles that went through, that were detected on each, and then from each side. And from that, he could tell deflection angles. Oh no. Okay, cool. I don't want that. All right, so Rutherford, we did that already. So we're basically done. So we talked about this already. Protons, the charge and the mass is here. Not really too important. Again, these are more physics constants. We're not going to really use them in this class. And also, another thing that's important that actually me taking that mass spec class taught me is that when you add up the, so let's say you have one atom of, I don't know, of hydrogen. All right, I want to find the mass of hydrogen from the mass of adding the proton and the electron together. That's not how it works. You can't add up the mass of the subatomic particles that are in an atom to figure out the mass of the atom. Because the formation of an atom releases energy. And that energy, E equals mc squared, is from the mass that's converted. So it actually loses mass as it's formed. And that mass is transformed into energy. So when you form an atom, it's actually a little bit less than the sum of the components. Fun fact. Okay, so neutrons, we get it. Oh, the Rutherford had a problem. He couldn't detect the neutrons. And then this guy was like, oh, just process of elimination. Neutrons. Cool. All right, so there is the summary table of the subatomic particles. And that's really it. So chapter 2 homework is due the end of next week. Yes, so the next week, midnight, after this class. Subscribe on YouTube. There's my thingy, and then follow Crash Chem and Instagram. So I'm going to stop the recording now. You can still ask questions, but I'll stop it. Stop recording.